We're going to talk about partitioning up the space of inputs to create a good test suite, a set of examples we're going to use to try to decide whether or not our code is bug-free. The first tool we have is what we call black box testing. And black box refers to the fact that it's just a box covered in black so we can't see inside of it. So here the test suite is designed without actually looking at the code. Nice thing about this is it can be done by someone other than the implementer. So we could have quality assurance group that's actually going to design the test suite here. And one of the nice advantages there is that often can help us avoid inherent biases. As an implementer, when I design code, I may be assuming that I'm always going to run this on positive values, for example. But if I don't build that into the specification, and I don't build in checks for that, somebody else may come along and try it on a negative value and expose the fact that I have a bug inside of my code. So that lack of bias, that lack of implicit bias is actually a great plus. The other thing that's nice is that the testing is designed without knowledge of the implementation. Since it's built just on looking at the specifications for the problem, I don't know how it's actually encoded. That means that that same test suite can be reused even if I change the implementation. That's actually nice. That sort of separation of the details of the implementation from the use of the implementation. That abstraction is an important part of how we build modules. And testing should take advantage of that. And indeed, black box testing will. All right, now let's look at what does it mean to do some black box testing. So let's think about a specification. Here's a piece of code. And again, here I'm actually just showing you the spec. I don't know the details of it. This is square root. And it says squirt takes in two values, x and epsilon, and it assumes they're both floats, that x is greater than or equal to 0, epsilon is greater than 0, and it's going to return a result with a particular condition in the end. Okay, what are the paths through the specification? Well, if I look at the spec, I can see that x, there are two conditions basically. I can separate out when x is equal to 0 from where x is greater than 0. And I could, in principle, just create two test cases, one for each one of those. But I kind of know that's not enough. So the spec itself is simply giving me a first pass at how I might try and test it, but I might want to think about other places in which I want to refine that idea. Okay, what does that mean? Well, let's think about this. It's often good not only when I'm thinking about paths through the specification to think about just the possible paths, but to think about the boundary cases. As an aside, if I have an input that's a list, what are the boundary cases I might want to think about here? Well, the list could be empty, the list could have one element, or the list could have many elements. Difference between 2, 3, 4, probably not as crucial, but the difference between 0, 1, and many, that's a nice set of boundary conditions to think about. For numbers, we can do similar things. It's not just is it 0 or positive, it's also what happens if the number is very small, what happens if the number is very large, and what happens in the typical case. And I'm going to put quotes around typical because I'm going to have to think about different variations of what it means to be typical based on the specifications of the problem. So if we go back to my square root example, we can actually think about this then. What might be good test cases to use here? Well, I've put a little table together here, and these first four are what I would think of as typical cases. Okay? Notice, in all cases, I'm using epsilon to be pretty small because I want to get answers that are close to the right answer. That was part of that specification, that the difference between the actual value and the value I guessed at should be very close to what I want. And then notice what I've got. I've got from the spec the case of 0 and then the case of positive things. And I've picked out other things. I've picked out a perfect square. I've picked out a square whose root is irrational. And I've picked out one where the input is less than 1. Because I know for numbers, and especially for square roots, there's often a difference between fractions and numbers bigger than 1. I've selected 4 good typical examples. The second thing I've done is I've looked at some examples that are a little bit different. And the first one right here is one where I'm still taking a simple example, but I'm taking a very small epsilon. That is likely to stretch my code. What happens if I have something that is really, really small? Okay? And then I'm looking at examples where I'm either taking really small or really large values, both for x and for epsilon, and I'm trying those out. So that's into that very small, very large, as opposed to the typical case. Now, in these last 5 extremes here, if I in fact find a bug, one of the things that will be interesting is that the bug might be inside the code, or it might be in the spec. For example, don't try and find a root if epsilon is really tiny. But it'll at least expose, do I have a problem or not? So there's a partition. This right here is a nice partition of the input space, and it has both typical examples and boundary case examples. And that is a nice example just based on black box testing of looking at what is the specification, what might I do.